This video is going to discuss a particular way of finding a solution to a differential equation. The method is going to be known as separation of variables. Previously, in our study of antidifferentiation, we saw differential equations of the form this. Okay, so it's an instance where y prime is isolated, or everything containing y is isolated to one side of the equation and is only represented as y prime. And then the right hand side, if you look at this carefully, this is all a function of x. Okay, so we could find the solution just by taking the antiderivative of every single term. So y of x would equal positive sign of 2x over 2 plus x cubed, and so on. You would just find the antiderivative, and then remember your constant. But you'd go ahead and find the antiderivative of each term, and that would be your solution. The method of separation of variables, what we're going to see is something that looks like this, where we have the derivative is equal to something that contains two functions multiplied together, where one function contains x, the other function contains y. Okay, or any variation of that. We could have them on same sides. We could have the x with the derivative, whatever. It's what we're gonna do is try and separate it out. So we want to get all the variables of one type. So this is like x or y to one side of the equation and all the others to the other side. Okay, so get the variables isolated and then integrate with respect to that variable on that side. So just heuristically what we're going to see, so we're going to be given something like this, separate it out so that everything that contains y, and so I switched to h because what we would have to do here is divide by g of y. We would have to divide by g of y, and I'm just representing that 1 over g of y as h. Okay, and then simultaneously I would have to multiply by the differential dx. Okay, and then I get this statement. Then I would integrate each side. Okay, so applied an integral to each side, and then I get out the antiderivative of little h, which is big H, antiderivative of big F, or little f, which is big F, and then the constant from integration. So here the variables would be isolated and antidifferentiated. I would have my solution. Okay. Now, 4 steps in practice, let's do it or 4 steps in theory, let's do it in practice. Alright, so here we want to find the general solution of the differential equation, this. Okay, so notice that I'm going to circle all the terms corresponding to y, so I need to make sure those are on the same side, and I need to make sure that, well, at least the t's are on the same side. The question is, what do you do with the constant? What do you do with that 2? The negative 2. The negative 2, we have a tendency of grouping that with the independent variable, or t in this case. If there's x's, you'd group it with x's, but generally you put any constants with the independent variable. So if I separate this now, I would have to multiply by y squared to both sides. Okay. And I'm just going to do this one step at a time so we don't lose track of the algebra. Y squared dy over dt is equal to negative 2 over e to the minus 4t. Okay, and just to make my life easier, I'm going to bring this up and I'm going to write this right hand side as negative 2 e to the 4t. Okay, next step, I'm going to multiply by dt to both sides. Okay, and then my resulting equation is going to be y squared dy is equal to negative 2 e to the 4t dt. And at this point, we're separated. Okay, all it took to separate this stuff was algebra. Okay, so notice that all the t's are on one side and all the y's are on the other. Okay, now I can apply an integral to both sides. Okay, and then I treat each side as its own thing. So if I ignore the right hand side completely, the antiderivative of y squared, well, that would be y cubed over 3. And then the right hand side, now ignoring the left side completely, the antiderivative of this would be negative 2e to the 4t over 4 plus c. Okay, and then the solution, we always should isolate x. So next step is isolate y, or the dependent variable. So multiplying by 3 and reducing, I'm going to have y cubed is equal to 3 times, and let's see, this is going to be negative 1/2 e to the 4t plus c. And then just going through and cube rooting each side. Okay, so I would raise each side to the 1/3 power, or cube root. It's going to be the same thing. But y is going to equal 3 parentheses, bracket out here, negative 1/2 e to the 4t plus c, all raised to the 1/3. Now, the question is, can you multiply the 3 through? Yes. Just make sure that, so if you did that, it would look something like bracket negative 3/2 e to the 4t plus 3c to the 1/3. Okay. So that's an example of separation of variables. What we did, just to review briefly, we looked and saw that there were two types of variables, y and t. I tried to get all the y's to one side and the t's to the other. I was able to do that, got them separated, integrated both sides with respect to the variable that was appearing on that side, found the antiderivative of each, worked it through, and got my solution. And either one of these forms would be allowable. Okay, moving on to another example. So now we want to find a particular solution. So we're given this boundary value. Okay, so let's go ahead and separate this thing. So I see the y's are here, and then I'm going to chunk the 3 with the sign together. With differential equations, it is really important to rewrite any Leibniz notation, or sorry, any prime notation in Leibniz notation, so that we can see the variables. Alright, so going through this one a little bit faster, separating this out, I need to divide both sides by y. So I'll have dy over dx times y is equal to 3 sine of 4x. And then multiplying both sides by dx to separate this thing fully, dy over y is equal to 3 sine 4x times dx. And going ahead and finding the antiderivative of each part. This is natural log of the absolute value of y is equal to, so this is going to be negative 3 cosine of 4x all over 4 plus c. Okay, and then now to isolate y, I would need to exponentiate each side. So take e to both sides. And I can write this as absolute value of y, or really we can just write it as y. Let's just write it as y is equal to e to the negative 3 cosine of 4x over 4 plus c. Now, technically by the rules of, or laws of exponents, we could, if we chose to do so, rewrite this as e to the 3 cosine of 4x all over 4 times e to the c. And then this, we could name that maybe another constant, big K, and then we would obtain the solution, big K e to the negative 3 cosine of 4x all over 4. Okay, that would be another form of the solution, the general solution. But now I want to find the particular solution using this boundary value. So we know that y of pi by 4 is equal to e to the 3/4. Okay, so now what that means is I'm going to plug in, so this is going to be e to the 3/4 when I plug in is equal to k e to the minus 3 cosine of pi by 4 times 4 all over 4. Okay, and I think what I get, so pi by 4 by times 4 is pi. Cosine of pi is -1, so that's positive 3/4. So this is e to the 3/4 is equal to k times e to the 3/4. So that just implies that k is 1. Okay, which leads ultimately to the solution y is equal to just e to the minus 3 cosine of 4x all over 4 as my particular solution. Okay, again, what we found back here, this was the general solution. Alright, so again, we applied the same properties and we did a little bit more algebra. Our last example that we're going to discuss is an application example. There are a lot of applications to differential equations, and some of them involve solutions via separation of variables, some don't. The module notes that accompany this course do have a few other examples that I encourage you to explore. Okay, so in the case of exponential growth and decay, we know that the change in the quantity, so the quantity I'm going to say is A, so the change in that quantity I'm going to say due to time is dA dt, is proportional to the amount of quantity present, so it's proportional, that's my constant of proportionality, to the amount present at any time. Okay, now we can actually separate this, right? So I see that there's an A and then there's a T, which I'm going to chunk with a constant. So if I separate this, you can verify the algebra on your own, but this is dA over A is equal to K dt, and when I find the antiderivative of each of these, this ends up being natural log of the absolute value of A is equal to kt plus c. Well, then to exponentiate this would be the next step, and I get A is equal to e to the kt plus c, and applying that same separation method, I can write this as e to the kt times e to the c via laws of exponents, and rewriting this again using this as, let's use a different constant, let's use m, I don't know, because k is already taken here. So rewriting this now, this is A is equal to m times e to the kt, and then if I know initially, so at time 0 I have A naught, I can use that and say that, okay, A naught is equal to m times e to the k times 0, and this is just 1, so that implies A naught is equal to m, And then I get, from here, I get the particular solution. A is equal to A naught e to the kt. And that is an equation that we've seen before when we were discussing exponential growth and decay. One other thing that I'll just mention is if we're given a time value, or half-life, half-life is a time value such that there is half of the initial amount remaining. Just a little refresher. And again, the last thing that I'll say is see the module notes for more examples on separation of variables. In particular, it's problems involving half-life and Newton's law of cooling.